Good morning, afternoon, or evening. How you all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we are going to continue with triangles. Surprise, surprise. As you can see, Chapter 3 has a lot of triangles involved with it. And today we're going to learn about the types of triangles. This is going to be information that we're going to use pretty much like everything so far throughout the whole year. Now, I know you've probably seen or been exposed or even learned the types of triangles before, but we're going to make sure that you really understand everything today and really solidify your knowledge about all the different types of triangles. So let's get right to it. Okay, guys, the first thing we're going to learn about is a scalene triangle. And a scalene triangle, as you can see from the example right here, is a triangle which has no congruent sides or angles. Remember, never assume perpendicularity or that sides are equal by an image. You always have to prove it. And as you can clearly see here, this is a side that is 10. This side is 8. This side is 12. And you may be thinking, wait a second, but how is that side 8? It looks longer than 10. That's the whole point, okay? You have to go with what is given, what is proven, all right? And as you can see here, we have an angle that's 30, we have an angle that is 50, and then we have an angle that is 100. So a scalene triangle is a triangle which has no congruent sides or angles. Number 2, an equilateral triangle. Think about the roots here. Equal. Okay, that's equi is like equal. An equilateral triangle, surprise, surprise, is a triangle which has all sides are congruent. Okay? And as you can clearly see here from the figure that I have provided, AB is congruent to AC, which is congruent to BC. So a triangle in which all sides are congruent is called an equilateral triangle. Equilateral. Number 3, an isosceles triangle. Well, you can pretty much get the definition from the figure here. And as you can see, I have these angles over here on the left and a segment. So there's a little bit to what goes into an isosceles triangle. And an isosceles triangle is a triangle that has 2 congruent sides or legs. Hence, in my figure, AB is congruent to AC. And 2 congruent base angles. Again, as you can see in my figure, hence, angle B is congruent to angle C. And if 2 legs are congruent, then the 2 base angles are congruent, and vice versa. This is called the base angle theorem. It's not really in your book, but it is called the base angle theorem. And again, it states that if 2 sides or legs of a triangle are congruent, you can automatically guarantee that the 2 base angles are also congruent. And then hopefully you remember what converse means. Converse is when you flip it around. You can have the converse of the base angles theorem. And the converse of the base angles theorem states that if the base angles are congruent, I'm highlighting them in green now, if the base angles are congruent, then the sides or the legs of the triangle are also congruent. So a lot of powerful stuff here. Okay, a lot of powerful stuff. So an isosceles triangle, again, is a triangle that has two congruent sides or legs and two congruent base angles. If two legs are congruent, then the two base angles are congruent, and vice versa. That means that if two base angles are congruent, then the two legs are congruent. Okay? Now, let me explain what this over here entails. I'm going to erase all of this for a second now. Okay. Angle A. Angle A, as you can see, is the pinnacle. It's the top. It is called the vertex. Okay? That is the top angle. That is the pinnacle of the isosceles triangle. It is directly opposite the base of the isosceles triangle. Since BC is the base, then logic would dictate that angles B and C are the base angles, because they are the angles that attach the base to the two red legs AB and AC. Okay? BC, therefore, is the base. And AB, here in red, and AC are called the legs. All right? So I really need you to understand this. So I hate to be a big repeater and a broken record, but we're going to just make sure you understand all of this. A is the vertex. A is across from the base, which we'll highlight in red, which is BC. That is the base. How do you know it's the base, Mr. Morrow? Because the legs, which are here in blue, of an isosceles triangle will always be congruent. So that third side that is not congruent to any of the other sides has to be the base. So AB and AC are the legs or sides, but let's go ahead and call them the legs. And the base angle, or base angles rather, are the angles that attach the base with the legs. A lot of stuff going on with the isosceles triangles, very important. Okay, let's move on. Number 4, equiangular triangle. Well, you could immediately know the definition by looking at the figure here and think about it. Again, equiangular triangle. And that is a triangle in which all angles are congruent. Now, just to give you a little bit more information, if a triangle is equiangular, then it is also equilateral, and vice versa. So, see how the angles here are all congruent? We're going to study later in a couple sections. It's called the angle-side relationships. And basically, if the angles are all congruent, that means that the sides are all congruent. So if a triangle is equiangular, it is also equilateral, and vice versa. If a triangle is equilateral, then it is also equiangular. Okay? Very, very important. Now, let's continue with angles. Okay, we know the types of triangles due to sides, and now we're talking about the types of triangles due to angles. An acute triangle, you could pretty much get the definition by looking at the figure. A triangle in which all angles are acute. Please remember that an acute angle is an angle, we'll call X, that is greater than 0 but less than 90 degrees. Okay? It's got to be greater than 0, but it has to be less than 90. It cannot be 90 degrees because then it would be a right triangle. So an acute triangle is a triangle in which all angles are acute. In other words, between 0 and 90, greater than 0 and less than 90 degrees. An obtuse triangle. Be careful with this one. A lot of times people will say, oh, it's got to be the same as an acute, but opposite. All the angles have to be greater than 90. That's impossible. Because remember that a triangle only contains within it 180 degrees. So you can't have more than one angle that is obtuse. Hence the definition of an obtuse triangle. It is a triangle in which one angle is obtuse and only one angle. Please remember that an obtuse angle, okay, is an angle x which is greater than 90 but less than 180 degrees. It cannot be equal to 90 because then that would be a right angle, and it cannot be equal to 180 degrees because then it would be a straight angle. So an obtuse triangle is a triangle in which one angle is obtuse. Right here, that's my obtuse angle. And 110 plus 30 plus 40 does equal 180 degrees. Remember that a triangle contains 180 degrees. We should have done the same comparison with my acute here. If you do 60 plus 40 plus 80, that will also equal 180 degrees. That cannot fail. A triangle must have exactly 180 degrees contained within the sum of its angles. So an obtuse triangle, once again, is a triangle in which one angle is obtuse. A right triangle. It doesn't matter if it's straight up like this ABC, or if it is inverted here like this ABC. A right triangle is simply a triangle in which one angle is a right angle. And if you remember, a right angle is an angle x which equals exactly 90 degrees. Please remember, we cannot assume right angles. We know this is a right angle because of my right angle indicator here and my right angle indicator there. So a right triangle is a triangle in which one angle is a right angle. Now, a couple things about the right triangle. AB, segments AB and BC, let me go ahead and color code this so it could be easier. Segments AB and BC, AB and BC are known as the legs. These are the legs. No, they are not congruent like an isosceles, but they are called the legs, or sometimes they'll say sides, which is fine. And AC, here in red, is what is called the hypotenuse. But tomorrow, how do you know the difference? Well, very simple. The hypotenuse, similar to the base of a isosceles triangle, remember that the base is exactly opposite of the vertex? Well, AC is always the side exactly opposite from the right angle. So over here, you have the leg AB and leg BC. And then across the 90, directly opposite of the right angle, you have here in blue AC, which is the hypotenuse. Very important as well. Okay? So now let's do some examples. Okay? These first two examples I'm going to prove in paragraph form. Remember, we rarely use paragraph form, but when we did learn about paragraph proofs, remember that I said sometimes it's easier just to explain in words in a little paragraph how you prove your conclusion. Well, in this case, I believe that it's a lot easier to go ahead and use paragraph proofs for these two particular examples. Given CBD, angle CBD, is equal to 70 degrees. I want to prove that triangle ABC is obtuse. Well, this is very simple, guys. If you remember, okay, angle ABD here is a straight angle. That means that angle ABC and angle CBD must equal 180. And if they equal 180 degrees, that means that angle B here, or angle ABC, there are three angle B's, so angle ABC is equal to 110 degrees. Why? Because 180 minus 70 equals 110 degrees. If angle ABC within triangle ABC is 110 degrees, that means that triangle ABC is obtuse. How do I put that in a nice, neat paragraph? Well, this is what I thought of. Since angle CBD, which is this guy right here, okay, is 70 degrees, and angle ABD is a straight angle, which we already defined that, then angle ABC must equal 110 degrees because of the subtraction property. Therefore, triangle ABC is an obtuse triangle by definition. Why? Because it has one angle that is obtuse. Okay. Hopefully that makes sense. Example 2. They tell us here that EG, okay, EG is congruent to FH. So EG is congruent to FH. Okay? Be careful here. Think about this one. They also tell us, though, that EF is greater than EG. So they tell us that EF is greater than EG. Okay. I want to prove that triangle EFG, which is this guy right here in green, is scalene. Well, this is pretty simple, but just think about what's going on here. Okay, I'm going to use some numbers to help you guys out. If EG, which is this guy right here, is congruent to FH, okay, let's just go ahead and put some numbers. EG, let's just say that that's 10, and let's say that FH, since it's congruent, is also 10. All right? But they tell me that EF, this guy right here, is greater than EG. So that means, let's say that EF is equal to 12. All right? Well, if EF is equal to 12, that means that EF here is different than EG. It's greater. And remember what we said. FH is congruent to EG. So what do we know about FG? Well, it has to be smaller than FH. So that is also going to be different. And now if you look at the sides here and the way I wrote the tick marks, none of the tick marks are equal, so that means none of the sides are equal. So that means that triangle EFG is scalene by definition. Hopefully the numbers made that a little bit easier for you. So let's put that into paragraph form. EG is equal to FH. Since FH is clearly longer than FG, which we marked with 3 tick marks in black, Okay, it's longer than FG. EG must be longer than FG. Since EF is greater than EG, therefore EF must be longer than FG as well. Since no sides are congruent, triangle EFG is scalene by definition. I think that using numbers here was the easiest way to really identify that. Okay? Hopefully that makes sense. Now let's get to the fun proofs. Okay. Alrighty here. Right off the bat, you can see we have some overlapping triangles. So let's use our skills from 3-5, and let's remember to try to extrapolate or isolate or pull out the two triangles that we are working with. We know that angle 1 is congruent to angle 3. Okay? 1 is congruent to angle 3. I just want to draw this out to see what triangles we're working with. We also know that angle 2 is congruent to angle 4. So right off the bat, think about it, because of addition property, we know that angle JKM is going to be congruent to angle OMK because of the addition property. And then they tell us that JP is congruent to PO. So JP is congruent to PO. And I want to prove that triangle KPM here, okay, is isosceles. Okay, let's think about what we were given here, and let's see what we can pull out. I would pull out JKM, if you think about it, and I would also pull out here in blue triangle JMK. So I'm going to pull these guys out right here. All right? Okay. So let's first start with the main triangles. We're going to work with both figures. Okay. Angle 1 is congruent to angle 3, given. Let's go ahead and label that, just like we did before. Angle 2 is congruent to angle 4. Let's go ahead and label that, like we did before. And now we know clearly that angle JKM, this guy right here, must be congruent to angle OMK, this guy right here, because of the addition property. The sum of congruent angles are congruent. Okay? So in our isolated angles here, we know that JKM, angle JKM, is congruent to angle OMK. All right. Next, if we look at the main figure, doesn't KM work as one of the legs of triangle JKM and triangle OMK? We can see that clearly here. KM must be congruent to KM. Why? Because of reflexive property. Okay? Hope everyone's with me here so far. Okay? Now, triangle JKM would be congruent to triangle OMK. Why? Okay, if you think about this, okay, this may get a little confusing, but I want to try to help you with both figures. Remember that we had stated that angle 4, which is this guy right here, angle 4, was congruent to angle 2. Well, when we isolated these two triangles, angle 4 is this angle right here. angle JMK. And that is congruent to angle 2, which is this guy right here, angle OKM. And since we know that KM is congruent to KM because of the reflexive property, we can see clearly that triangle JKM is congruent to triangle OMK because of angle side angle. Now there's a lot of stuff going on here, so I'm not going to redo the proof. I'm just going to redo the drawing, okay? We know that angle 1 was congruent to angle 3. We know that angle 2 was congruent to angle 4. Right there, think about it. Angle 2 from our blue triangle here, OMK, okay, that would be my angle 2. So that means that angle OKM is congruent to angle 4, which is my red triangle here, which is angle 4 right here, angle JMK. Okay? Then we proved, because angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4, that angle JKM, which is right here, is congruent to angle OMK, which is right here. And then we proved that KM is congruent to KM because of the reflexive property. And that's how I got to triangle JKM is congruent to triangle OMK because of angle side angle. So hopefully that makes a lot of sense to you guys. Okay? Now, if we go back to my original figure here, remember what you're trying to prove here at the end. You're trying to prove that triangle KPM is isosceles. So we know already that angle 2 is congruent to angle 4. Okay? And they also tell us that JP is congruent to PO. Okay? Well, then that means that KP must be congruent to MP because of the subtraction property. Now you may be thinking, whoa, wait a second. What do you mean subtraction property, Mr. Morrow? Didn't we already prove that JKM is congruent to triangle OMK? Right? So we know that JM is congruent to OK. So if they tell us that JP is congruent to OP, that must mean that JM is congruent to KO because of CP/CTC, right? And then we have JP is congruent to PO. That's a given. So therefore, KP must be congruent to MP because of subtraction property. So now we know that this guy is congruent to this guy. And now we can clearly prove that triangle KPM is isosceles because the definition of an isosceles triangle. Hopefully that made sense. Now, some of you may be thinking, wait a second, Mr. Morrow. Didn't you tell us that if the base angles are congruent, that means that the sides, that the legs are congruent? Yes, I did. If I already stated to you that angle 2 is congruent to angle 4, by definition, PK must be congruent to PM. So by definition, KPM is isosceles. So why did I go through this long proof? Because they're not always going to give you the information nice and easy, and I wanted to make sure that you can deduct from the given information how to prove that PKM is isosceles. So one more time, okay? I don't want to bore you, but I want to make sure you got this. Angle 1 is congruent to angle 3. Angle 2 is congruent to angle 4. Angle JKM is congruent to angle OMK. So that means that we know that angle JKM is congruent to OMK. Then we know also, and that's because of the addition property, then we know that KM is congruent to itself, so KM is congruent to KM. Because angle 2 is congruent to angle 4, we know that angle 2 here, okay, is OKM, and that's congruent to angle 4 here, which is JMK. Now we know that triangle JKM is congruent to triangle OMK. Because of that, we know that JM is congruent to OK because of CPCTC. Then since they tell us that JP is congruent to OP, we can clearly prove that PK is congruent to PM because of subtraction property, step 8. And then if we know that the base angles, which are 2 and 4, are congruent, and the legs are congruent, we have an isosceles triangle. Okay? And hopefully that makes sense. Hopefully you learned a lot. Thank you so very much, and have a wonderful day. Bye-bye.